So now we want to discuss about local lemma, robust local lemma. Okay, let's write the capital letter. So far we have dealt with several problems, and then we use probability method to prove them. And one of the recurring themes is that there are bad events, and with positive probability, we can avoid all of them. And how do we prove? We used union bound. For each bad event, we count the probability, and then we add them all together, and then they sum up to less than 1, then we are happy. But this union bound is quite weak. For example, I mean, if we have say, n coin toss, and then bad event is getting tail, then we know that we can avoid, I mean, all bad events. There is a probability that you get head, all of them head. It is very unlikely, but that is possible. That's positive probability. But what do we know? Ice coin toss has the probability of bad event is half. Then if you take the union bound, the probability that I mean, you get at least one coin toss which is bad is what you get this huge number which is much bigger than 1. So you cannot use union bound. Okay. But how did we know that in this case we can avoid all the bad events? We can do that because all coin tosses are independent. So we can directly compute the probability. First one is half as head, second one is head, third one is head, all of them is head is what? Up to the n, which is positive probability. So like this, if we have many bad events and then all of them are independent, completely independent, the outcome of one is not depending on any other outcome, then it's easy. As long as all those bad events probability is less than 1, then the avoiding it is always possible. You multiply the 1 minus the probability of bad event, and then you multiply all of them. It's always positive. Okay, but this is very, I mean, naive case. There are not many cases that those events that we want to consider are completely independent. And natural question is that what if those bad events are not really completely independent, but they have weak dependency? Then can we somehow say something? So this is a case that our situation is somewhat close to this kind of case. So intuitively, some coin tosses have some weak dependency. Then intuitively, then maybe this changes a bit, but maybe we can still say that it's still positive. Okay, of course, for this, we have to define what this weak dependency means. So let's define the following concept. So let A1 to AN be events. And we say a compound event is the event that specifies the occurrence of AI for certain I and non-occurrence of AI for some T where S and T are disjoint. So it just means that you consider this kind of event. So some of them happen, some of them don't happen. And then, yeah, that's, if you specify that, that's compound event. And we say that an event A is mutually independent of A1 to AN if this B is independent of each compound event specified by disjoint subsets S and C of this bracket. So this is the independence. This is saying that, so we know that what independent means in probability. The probability of B is same with probability of B, assuming, this compound event. Are same. No matter what you add here, so this is same, then they are independent. That's what mutually independent means. And this mutually independent is stronger than and just pairwise independence. So you consider this compound event, not just anything. So for example, let's consider this probability space with the 4 elements, A, B, C, D. And let's say X is the event that the A and B are here. And then, the probability of X is 1/4 for each element. And say Y is the event of these two, then C with the event of these two. Then what? Probability of X is half. Okay. Now what's the probability of X assuming Y? Out of these two, if you randomly choose it according to its weight, which are uniform, the probability that you get A is half, so this is also half. And probability of X conditioning on C is also half. So what does this show? Yeah, in the same way, you can show that the X, Y are independent, then X, G are independent, and Y, G are independent. So they are all pairwise independent. However, it is not mutually independent. Why? You consider the probability of X assuming the occurrence of Y and then occurrence of G. If you know that the Y occur and then G occur, then intersection is a C. So this specifies that our event is C, but assuming that the probability that we get X is 0, which is different from the probability of X. So this mutual independence is actually stronger than just pairwise independence. So this specifies, so this is the concept that we're going to use to state our main lemma, which is called the robust local lemma, and this is called symmetric local lemma. Ruled by Eldridge and robust. Let's say you have events A1 to AN. Such that each is mutually independent of some set of other events, but all but and most key events. So this A1, for this A1, there are the other events which may be, this AI may be depending on these, but for the rest of them, AI is mutually independent of these. So this specifies that the dependency is weak. If this D is small, then this is very weak dependency. If this D is 0, then they are completely independent. If this D is large, then the dependency is strong. So this D measures how strong the dependency is. And then we want to say that if this D is small enough, then we can avoid all the bad events. Suppose that the probability of each AI is mod P for all I. Then this is the formula to check the dependency. The E is 2.71 the number times P times D is smaller than 1. Then the probability that one can avoid all AI is positive. So this is the local lemma. So in such a situation, if you want to conclude that we can avoid all the bad events, you have to check this inequality. That's sufficient for us. Okay, so let's see an example. We can use this to improve the lower bound of the Ramsey number. So we show that this bound holds. So previously what we showed this bound using simple probability method. Then we showed this bound using alteration method, which are improved by square root of 2. And then, so this was, and then we improved this by multiplying another square root of 2. So this can be obtained from the symmetric local lemma. Although, in this sequence, we only improve by square root of 2 and square root of 2, multiplicative constant square root of 2. But this is best we know. Best lower bound on this Ramsey number we know so far. So we can prove this. So let's see how we prove it. So again, as before, we color the edge of complete graph on n vertices by giving its edge color red or blue independently at random with the probability half. Independently, uniformly at random. So uniformly means that the red and blue are equally likely with probability half. Independently means that each pair how you give them are totally independent. So now what? Again, what we have to do? We have to define bad events. So for each vertex, say f of size k, we define bad event. A bad is the event that the subgraph induced by S is monochromatic. Then what happens? So S, you have edges here. And yeah, so anyway, so I just drawn some edges of the complete graph. There are, of course, more edges. Then what do you know? If we know the color of this edge, or this edge, or this edge, that has no effect on the color zone here, right? So, knowing the color of all edges outside this S2, so even if you know the edges that touches S, it's irrelevant. That has no effect on the probability of AS. Hence, what? Let D be as in the local lemma. Then what? Let's say B, what would it be? This would be the number of other events which shares an edge with S. So that is the number of K subsets in bracket N at share at least 2 vertices of S. Then the event A sub S is mutually independent of the sets of all other events. Then how do we know this T? T is at most you have S, and then you choose 2 which will be shared, which is at most K choose 2, and then choose K minus 2 other things, which are N minus 2 choose K minus 2. So if you compute it, this is at most what? A squared over 2 times NE divided by K minus 2 and K minus 2. So using the we don't have to keep all the term. It will make the computation more complicated. So we can just write it this way as an upper bound on T. And what do we have to compute now? We have to compute. Now we have an upper bound on T. Now we find the upper bound on T, on P. We also have probability of this AS or whatever S is 2 minus 1, 2 to the 1 minus K choose 2. And this is our P. So to apply the robust local lemma, it's sufficient to make, so N is again, we didn't specify yet. But as long as this M is small enough so that this D, this upper bound on D is smaller than 1 over E times P. So meaning that the EPD is smaller than 1. And what's this? This is 1 over 2e and 2 to the k over 2 times 2 to the k over 2 to the a minus 2. Okay, so now what? Now you need to choose n so that this inequality holds. On the wire it holds this inequality, we want to make n as big as possible, which you can see that it's just computation. So this is sufficient. So you can take, n to be floor of this. And if you see it, what's this? As k goes to infinity, this is going to 1. So this is simply, you can just write it as 1 plus 0, 1. So this is the term that goes to 0 as k goes to k grows. So you can take n to be this number. And this shows that the robust local lemma ensures that you can, with positive probability, you can color all the edges, while it avoids the monochromatic click. Okay. So in the above events, if you see, in the above proof, if you see, how did we prove it's mutually independent? You have this kind of basis event of how you color its edges. And then your bad event is compound event of them. And then you have a compound event of this basis event, where these basis events are all independent. Then you have another compound event that does not share any basis element. And this is mutually independent of the other one, right? So that's quite a common case where you can apply the local lemma. And then also that's the reason why it's called local lemma. So you have many basis events. So in the above case, it's the coloring of its edge. And in this basis event, you have your bad events, which are compound of this. So this is your bad event. And then this is your bad event. And so on. In such a case, if all of these are completely independent, and this is mutually independent of this, as long as they don't share anything. This is mutually independent of these two, as long as they don't share anything. So when you compute D, we only have to count the ones that share something with this and share something with this. And usually these bad events, depending on small number of these basis events, of course, if all of them are depending on large set, then they are all dependent. So we cannot apply local lemma. So this says that this bad set is a local event, meaning that only small number of these basis events completely determines it. This is local event, not the global event, right? So when we can apply the local lemma, the situation is that these bad events are local bad events, then we can apply. That's why it's called local lemma. Okay. And that can be stated as this, mutual independence principle. That's a common recurring theme. So that we stated as this proposition that G1 will be GM be independent, so totally independent. So all of them are just independent experiments. A1 to AN the events such that if AI is determined by a subset Si of this event, this experiment. And if this Si is disjoint from, say, Sj1, union Fjk, then this AI is mutually independent of the corresponding events. So which is almost trivial, but this is the useful thing to state it as a principle so that later when we apply local lemma, we can just mention this to, so that we don't have to really justify the same easy trivial thing over and over again. So let's consider one more application of the local lemma. It's application to this list coloring. Okay, so list coloring, we previously showed that if you have a K-degenerate graph, or more generally, okay, K-degenerate graph implies K-1 is one choosable. And also we show the Brooks theorem, for list coloring, which said that as long as this is not complete graph and all cycle, you can save one, making it to K. So in those things, we only consider about the graph, and we didn't really care about the structures of lists. So we already assumed that the lists are somehow given in the worst possible way. In all those previous, proof of list coloring, we already assumed that your opponent give you the list, the worst possible list, then can you still do it? But what if we know that the lists are somewhat good? Then can we complete the coloring? For example, if those lists are extremely good, in a sense that if you have U, then B, a list of U and list of B are completely disjoint for all adjacent UB, then the problem becomes very easy. And choosing any color for B in UB, it gives you proper coloring, right? So this is the extremely good case. The lists are completely good, so there is nothing you have to do. But in this case, what? In this case, U, in other words, you have U, and then it's labeled. The coloring here does not appear in U, does not appear in the list for the labels. But this is too extreme. What if we weaken it? So a coloring here may appear in this list, but not too many times. Then can we improve it? And then what's the best? It's not that many times. And how, what's the best we can do? So regarding that, we can prove the following theorem. So let L be a list assignment for a graph G in which every list has size list K. And if every color appears in and most K over 2E, again, this E is 2.71 the irrational number. And most K over 2E of the lists in each vertex neighborhood. Meaning that whatever vertex you take, you see this neighborhood. And then C, for whatever color C, you see whether C is in the list, this list, and C is in the list of this vertex, C is in the list of this vertex, you count. And then you have at most this many. Then G has a proper color. Notice that here we didn't assume anything on G. G could be complete graph. So any vertex here might have many neighbors, but as long as that color does not appear more than K over 2E times, and it is okay. So we will prove it using robust local lemma. So first we assume that its list has size exactly K. It's not, you just delete them. I mean, that would not hurt anything. So now we form a random coloring. By choosing colors for each vertex uniformly and independently. Maybe writing independently works better. All right. At random from its list. And we define a bad event for X, Y, and then color C, which lies in the list of both things. We let A sub X, Y, C be the event that X and Y both receive color C. So that's the event that we want to avoid. As we want to obtain a proper coloring, this is the bad event. Then what? The probability of such a bad event is what? 1 over K squared, which is, let's it be P. Because this has exactly K color and this has exactly K color. We happen to choose C, and then that happens with probability 1 over K and over. So it's exactly 1 over K squared. Okay. So the occurrence of these bad events A, X, Y, C is determined by colors chosen for X and Y. So what? By the mutual independence principle, if A, X, Y, C is mutually independent of the set of all such events, the x prime, y prime, c prime, where x prime, y prime is not incident with xy. So, as in order to determine D, we have to count the bad events where x prime, y prime is incident with x, y. So, but what do you know? For on edge x prime, y prime incident to, sorry? Okay, sorry. Where were we? So when you have x prime, y prime, which is incident to xy, the event ax prime, y prime, c prime is defined if and only if the c prime is in the list of x prime and then list of y prime at the same time. So suppose you have x, y, and then y prime, and then let's say x and x prime are same. So let's say by symmetry, suppose x and x prime are same, and then y and y prime are different. Then what? The hypothesis of the lemma allows what? At most. So this c prime, in this case, must be in the list of x, which is same as the list of x prime. And then for those color, how many of them are actually in y prime? Is that it's hypothesis. So there are many choices of y prime here. And for this specific c prime, we get at most k over 2e such events for its color c prime in this list. And actually one of which is eliminated as xy, the original one. And the same conclusion holds for the h incident with y. Then what do we get? Then D is at most. So how many choices for are here? We choose c prime, which there are k choices. And then for each of them, we have this. So what? K squared over 2e minus 1. 1 is eliminated from this. That's for x. That's for the case that the x is shared. And then that the other for the edges incident with y. Say this is smaller than k squared over e. At the this is smaller. So what? Each event ax, y, c is mutually dependent of a set of all but k squared over e one, all but d of the other events. So then what? Since E times P times D is what? E times P was 1 over K square, and then D is K square over E, then this was tricky equality, and this is 1. So what's local lemma? Implies that there is a coloring, that no bad events happen, no events AX, Y, C equals. Hence, this is a proper coloring, proper L coloring exists. So this proves what we want. Okay, so this shows that this is the here. I mean, intuitively we said that if any color, every color in here does not appear in the list of the neighbor, or not, I mean, it appears but not that many times in here, then we could complete the coloring. So this theorem implies that. But the next question is that, okay, would it be best possible? Can we do better? And it's easy to check that the K is not possible. So this cannot be improved to K, but Reed and Sudako in 2002 proved that we can improve this to 1 minus 0 1 times K. So instead of K over 2E, it can be very close to K. And then Reed conjecture that even K minus 1 might be sufficient. Okay, so that was the introduction of this robust local lemma. And if you see it in here, we stated this local lemma as a symmetric local lemma. Then one might ask that is there a non-symmetric version? And yes, there is a non-symmetric version, and then we will talk about this in next video. Okay, then I will see you in next video.